You okay with that? All right. I'll delete it if it's awful.
It will be. Okay. All right.
Well, your position equation is going to be when you cosine of omega t minus phi, which can be simplified to a cosine of 2 pi times the frequency times the time minus.
Okay, slow down. 2 pi.
Bracket.
What?
The other bracket.
Where? Here?
No. Okay, well,
Sorry.
in the quantity, frequency times the time minus your position of the wave over lambda. Pretty sure I have that equation, I'm just checking. In this case, I said the position was h.
Okay, so go back. Where did I screw up with the brackets? Is it here?
No.
Okay.
Minus h.
Minus 8.
Over lambda. So you take the derivative, which is just negative times your frequency times the sine of the inside joke. Times the time. Remember I had it.
Here?
Okay. And then you square it to get your velocity squared. You're missing a pi.
What?
You're missing a pi.
Oh, yeah, I erased it. Sorry. It's a jumbled mess there.
So you can square it.
Yep. So square this. Plug that in there. Okay.
And then you calculate the energy across one wavelength.
Okay. Everybody.
How did we get to this point?
We don't know h though, so how would you find v from there? Are you just going to use the h cancel?
Along with the area.
Yeah, so let's talk about the different
Okay.
variables we got here. So, 2 pi, clearly. What's A?
Amplitude.
Amplitude. F. Frequency. So then we got time. What's H? Okay. Is that given to us? No, so as we said, we hope it cancels, and it does.
Well, in the context of a problem, if you simplify a position equation like that, or I guess it's not more simple than the previous one, but if you change it to be that way, x is the position of the rest of the wave, and the height being the distance from the origin, h, and because the force is perpendicular to the direction of the wave, you can consider h to be the x position. But I guess it's in common function because it
Yeah.
Where would it cancel out? I'm just a little still confused.
Because you're going to do it over the, when you do, right, when you do the integral over the wavelength, they don't go away.
Oh, okay.
Why not?
Because it's cool.
So,
Especially for
I'd like-
the camera, come on.
I'd like to
So,
understand.
go from there.
We'll keep it secret. Keep it safe.
Okay.
So, I recognize the A cosine omega t minus b. That's like our small oscillation.
This one?
Yeah.
Okay.
So, are we just recognizing that this is an oscillating system, and so we're using that?
This is can also be described as the wave equation. So if you tracked simple harmonic oscillators, they would follow that sinusoidal path. And so any simple harmonic oscillator can be described through the use of waves or sines and cosines.
Okay. And then we start transforming it there. I see we're plugging in for omega 2 pi. I guess that kind of makes sense. And phi is h over lambda. Is that what that is?
Okay?
2 pi h over lambda. Yeah, that's distributed.
2 pi h over lambda.
Okay, why?
I don't know. Just asking.
Find it.
Well, omega is equal to 2 pi f, right? And then I don't know about phi.
2 pi f.
2 pi h over lambda.
So why is there an inner bracket?
Because he just factor out the 2 pi.
Just factor.
Oh, because they both had 2 pi. Okay.
So omega is 2 pi f. And it's 2 pi
Okay.
h over lambda. I don't know.
What is phi?
2 pi h over lambda?
No, I'm just asking
Like
what's
what
the
is it?
general definition. What, in this equation, if I just use this, what is this?
It's the phase angle.
Okay, what's that?
And that's where it starts.
Yeah. So,
You just kind of pick a starting point, and then depending on where you picked, it could be a sine wave or a cosine wave.
yeah, or just anywhere in between. So, I mean, if you start here, what is,
Sine.
yeah, it'd be sine, but for our setup, what would it be?
Pi has.
Okay.
0.
So then if we picked it here, what would it be?
Cosine. Or 1. Or wait, I don't know.
0, pi, no, not pi, 2 pi. Pi would be the negative side of it, right? So then how does 2 pi h over lambda relate to this? How are they connected?
So K,
It's repeating every 2 pi. And the h would be kind of like the radius? The height of the wave?
Just how long the bar is, just kind of figuring out what this is just you're figuring out a proportionality here that you're going to use with 2 pi.
What is lambda?
What?
What is h? What is lambda? I'm sorry, you're asking me. I don't know.
Anybody?
lambda.
So it's like thinking like you have the bar, I'm just kind of thinking out loud, but you have like a bar, you're dividing it by a bunch of wavelengths, so you're finding how many wavelengths are in that the bar, right?
Okay.
And then you're timing that by 2 pi, which will give you like 2 pi times the proportion of the bar that is a wave,
Okay.
which is where it should start.
Okay.
Does that sound okay?
Does anybody else want to try to explain it? No?
clear to me.
Well, lambda is 2 pi over the wave number. And in this case, it's simply only have one wave following the entire thing. So, we have like pi is the 2 pi times h over lambda.
Third number's K, right?
Yeah, wave number.
K is equal to 2 pi over lambda.
What was K?
2 pi over lambda is the wave number. Wave number.
Wave number? Wavelength?
What?
What's K? Supposed to
The
represent?
wave number.
What does that mean? It's a wave number.
Okay, so another way to write this is to not use this, but rather KX.
We have X, sorry about that.
What?
And then we have X instead of H, sorry about that.
Yes. Well, okay, KH. Well, in that case, general equations.
So it'd be K.
But we're not given a specific length of the bar for this, and so this typically tends to be a good conversion for it to go. Use that offset to then take it there. Does that make sense now, how we got to the,
Yeah.
to here?
Yeah.
Somewhat?
I don't know where to go from there though, but yeah. So,
Okay,
sweet.
let's go a little farther. We've got this, so.
Wait, what's going on at that sentence? I don't even know.
Just took it directly. Also use velocity. That's it. That's all we have. And then you can plug it into 1/2 mv squared.
Okay,
But I don't know.
so B squared is equal to 2 pi A Fs, or F sine 2 pi X B minus H over lambda.
That's all right.
And you have to
Well,
square
yeah, I was
it.
going to do the quantity square.
Oh, okay.
No, that's right.
I just didn't want to try to do it all to start with. So, simplifying it down, 4 pi squared, A squared, F squared, sine squared, 2 pi, F, B minus H over lambda. Okay, so we've got that now. And we've got, how do we find our mass?
Density times volume.
What was that?
Density times volume.
Okay,
So,
Well,
Yeah.
volume is area times h,
okay.
but because you're, but you're gonna have to integrate over the wavelength because this gives you the energy at a point. So when you do integrate across the wavelength, it's in terms of h. So you have dh instead of h.
Okay. So to do it, typically in these problems, if you're presented with this, you know you're going to have to convert it to that. Okay? So, now we integrate. Where is this getting us doing the integral? I want people to be able to think about that and explain that. Because otherwise I'm just doing math. Might as well be in calculus.
So if we're we're taking the area times the height, that gives us, and then multiplying it by the density, why wouldn't that give us the mass
That
by
would.
itself?
But we
Why
don't,
do you
we don't
have
have
to
age.
A section, not those.
We want just a
Yeah.
section of it? Well, then why don't you just take the cross-sectional area? But what,
We also don't have age. So we gotta get DH integrated. Maybe. I don't know. We don't.
yeah, I guess,
Why
Or
are we doing integrals? Why are we doing any of this?
Okay, so taking it a step back, we have the 1/2 mv squared that we're trying to solve for. And we're trying to get the intensity equation, which is power over area. And power is energy over time. And so we want to get the energy, which is
Okay, so density is power over area equals energy over time over area. Okay.
so energy is equal to kinetic energy plus potential energy. And the analogy I saw was you could think of all the little planes of the bar being connected by springs. So the spring have potential energy is equal to the spring constant, and it is related to the spring constant, and the kinetic energy is equal to the movement of the spring. But since we're doing lots of chunks of the bar, there's always going to be a part that's maximized potential and a part that's maximized kinetic. And so if you just take twice the kinetic energy, you can use that in place of potential plus kinetic.
Okay. Okay. Seems reasonable. Ish. Anybody else? Ideas? Connor?
You have the energy, like, not the energy across the distance, because you get into a single point, not really go with it. So you integrate across one wavelength to get the total energy of the wave.
So basically this comes back to our velocity, right? Why we need to do the integral.
And the integral for intensity might have velocity a different way. Rather, you still need to put in a value for velocity somewhere.
As long as, to be honest, as long as you guys show decent math and thought process in this, I'm not going to crush you. Don't worry about it. I mean, you don't have to get one final right answer for this. What?
That was second needed intensity.
Yeah.
We said maybe that's not correct.
Well, I don't know if it's not correct. I haven't figured out the actual number yet.
Well, the intensity is usually on a log scale, so 7
Yeah.
digit numbers, 7 to 7. It's
not
7 point something.
I know you've been generous, I just wanna understand it for myself.
And this is, I mean, there's probably different approaches you can take to solving this type of problem. I mean, I've heard there's two at least out
That's
here.
the problem I have
now.
is Connor and I are doing it a different time.
Yeah.
See,
So we kind of taken one. So basically, it's this velocity that we found is for, what is it for?
It's for the individual.
It's for an individual piece, right? So we need to figure out the energy for the whole wavelength because, as was said, different points are going to have, different parts of the rod are going to have different energies at that specific time. Because some might be moving at different rates. And so we have
Oh,
to
okay,
take
so
over the
this is
whole
like,
wavelength to
so the DH is like one plane,
one little slice.
plane of atoms,
Yes.
and we want to integrate that over a whole wavelength, so we know the inner intensity of
So
the
we
whole
can find
wave.
the energy in one wavelength, and then we can take that and figure out time, or figure
Okay,
out
all right, I
the
get
power
it.
and all of that stuff.
That makes sense, okay.
So that's one way. There's other ways that you can potentially approach it, yeah.
You do actually need.
Where the potential energy, or the 2K.
You need to know that 2 times the kinetic energy of the time is
Yes.
power. In order to finish this.
Yeah. That's, okay, so why
2 times the kinetic energy is what now?
Okay, why do we use that?
His equal to potential plus kinetic.
This is a fairly
Because the
important
change of kinetic energy is the work. No, I don't know.
Do you want to explain it again? Why you need
Okay,
to?
so we want to solve for the intensity, that's part of the problem. Intensity is power over area. Power is energy over time, so intensity is energy over time over area. The energy you can solve for, energy is always potential energy plus kinetic energy. And in this case, the bar, there's a restoring force pulling it. If a part of the bar is vibrating upwards, there's a restoring force pulling it downwards, and so that's the potential energy. But for each restoring force potential energy, there's going to be, when the bar is at its medium point, there's going to be the same amount of kinetic energy at the medium point. So we're looking at 2 different parts of the bar. One is fully up, one is fully at the center. And those energies are going to be equal because conservation of energy.
So at
So
the
instead of saying energy is potential plus kinetic, you could say energy is just twice kinetic.
because well, in that equation, potential when kinetic is at its highest, potential is 0.
Yeah.
But when potential is at its highest, kinetic is 0.
And so they have to equal each other. And so for the total energy, it's twice that. Twice the kinetic over the whole bar.
Twice because of a full wavelength?
Yes,
Or-
because half of them are going to be at the max potential and half of them are going to be at max kinetic. Approximately. I mean, clearly there are going to be gradations in between as you look at the whole wavelength of the bar.
Sure.
But
But
simplifying it down.
sums up to
Yes.
2 of them. That's cool.
Okay. Any other questions now that you almost have pretty much the whole thing?
No, we don't. No, we don't.
No, you don't. You got a good job now.
I don't know how to do this.
Any questions on this?
You're good, Mark.
What?
You're good. I don't know how to do this still. So you're good.
Good times. Sometimes I feel like if I try to be vague in going through these and having you guide, I just end up confusing the issues.
Yeah.
Unfortunately.
Yeah.
So sometimes I think you guys are better off not asking me to try to help because I don't want to try to give too much away. So it just gets more confusing. But
You should just give it away.
I should just give it away.
Yeah.
Okay. So, we talked some about sound waves in a tube and air and all that stuff. Do you guys want to kind of, Connor, yes.
I just want to point out that the Ford's equations are wrong
Oh, yeah, that's good.
for that one that we did the string.
Okay.
So like, I don't know if anybody
The
else-
plucking the string one?
Yeah, this phi equation is wrong. So that makes it a lot of dollars. You have to drive yourself.
Okay, so let's correct that then for sure. So where I don't take notes, so who has that? Then we can help correct that. Because yes, if you gave the wrong equation, then definitely need to fix that.
So